No, we're going to start with Macarena. She's first given to give an overview of her company. So yes, I'm sorry again, Macarena. I'm going to give you the screen.
So hello everyone. First of all, I would like to thank CTAQUA for inviting me to participate in this webinar. My name is Macarena Algarín. I'm co-founder of the company Estero Natural. That is a company dedicated mainly to oyster cultivation and ecotourism. So I'm here today to talk about IMTA in the Southern European Atlantic area, and specifically the advantages of its implementation according to our company's point of view. I have divided the presentation into 4 points: aquaculture in the Southern European Atlantic areas, aquaculture in esteros, and I will explain later what is an estero, Estero Natural, and the advantages. Estero Natural is the name of my company, and the advantages of IMTA in esteros. So I'm going to start giving insights about our context. Well, most of the aquaculture facilities in our area are land-based facilities. So this is due to our sea conditions, the Atlantic Ocean. So, okay, we have land-based facilities, and we have divided into 2 types. Esteros is a Spanish name, and others. And others include hatcheries, nurseries, and intensive fish farms. So according to our government data, we have 108 esteros in the south of Spain and in the south of Portugal, in Algarve, comparing with other facilities which are 19. So just said in another way, we have 85% of esteros compared to 15% of others facilities. That's why I'm going to focus on esteros. So, but what is an estero? So esteros are all salt production areas which were transformed into marine fish cultivation areas after the 70s crisis of the salt industry. So, like always, opportunity arises during times of crisis. And how does esteros work? Well, esteros use marine water. The water goes into the ponds through sluice gates, and water flows from pond to pond or by channels by gravity. So this process is completely influenced by the tides, because during the high tides, estero water comes to the estero, and during low tide, water released to the sea or to a bay in our case. So in this process, a water flow is generated, which is crucial to implement IMTA. And in spring season, when water comes, fish come as well and grow in a natural and a traditional way, because we don't use a pump and we don't feed fish. But which is the situation of esteros? Well, the situation is not good. If you compare these 2 pictures, on the left side, you can see a picture from the 50s, and on the right side, you can see the current situation, and you can see the structure of the esteros very damaged. You can see better in these 2 pictures. And this is a very worrying situation, because estero hosts a lot of biodiversity, a lot of species, a lot of birds, and some of them are threatened species. So we think that only with productive activity will we be able to stop the deterioration of the esteros. But which is the productive situation of esteros? Many companies realize that extensive fish farms are not profitable, and many of us cannot do another kind of aquaculture due to we are working in protected areas. So we think that we need companies' diversification strategies. And this is where integrated multi-trophic aquaculture can play an important role. So briefly, I'm going to talk about Estero Natural. We are located in Puerto Real, in Cádiz, in a natural park, el Parque Natural Bahía de Cádiz. We have 8 esteros, but we only can manage 2 or 3 esteros due to the other ones are very damaged. But overall, we have 200 hectares. If you see this picture, if you see the yellow area, this is where CTAQUA developed its pilot action, and that Erik will explain later. Our main activity is the sustainable cultivation and marketing of esteros products. Our secondary activities are ecotourism or nature tourism, R&D activities, environmental education, and gastronomy. So in short, we have 2 pillars: extensive aquaculture, mainly with oysters, and sustainable tourism. And we think that after CTAQUA implemented the pilot action, we think that integrated multi-trophic aquaculture can have advantages for these 2 pillars. So I'm going to talk about that very brief. As I say before, CTAQUA is going to explain the pilot action, but mainly they cultivate sea bream and oyster and algae together. So for one of our main pillars, the sustainable aquaculture, we think that IMTA can be very good to diversify our products, to improve our yields, to know a new system to cultivate oyster, because CTAQUA brought a new technology from IPMA in Portugal, and we are using now, and it's very good, this kind of system, and of course for environmental improvement. And for our other pillars, environmental education and tourism, when we explain what is IMTA to our visitors, they enjoy a lot. So we think implementing in IMTA can arouse interest of the people, can give us a good image, and also we can diversify our gastronomy. For example, I don't know, using algae or using sea cucumber, or so. We think for sure IMTA has advantages for at least for us. So thank you very much to everyone for listening.
So the next presentation is going to be provided by Gabriela Oliveira of IPMA. She is first going to explain the earthen pond system used at IPMA and how they implement IMTA there.
I am Gabriela Oliveira, and this presentation is about towards a standard model for land-based IMTA mariculture for 2 cases from southern Spain and Portugal. And in the first part, I will speak about IPMA case from Portugal, and in the second part, Erik-Jan Malta will speak about CTAQUA case from Spain. In Portugal and Spain, aquaculture earthen ponds are adapted decommissioned salt ponds, most located in protected areas. The maps above show an overview of the location of salt ponds in the Atlantic southern Spain and Portugal in red boxes, as Macarena also said before. In the areas under environmental protection regimes, the yellow and light green areas. IMTA production can be appropriate for protected areas because of its sustainable approach to aquaculture, and the advantage is that it is a land-based system where species, compartments, flows can be controlled. aiming to develop a land-based IMTA standard model. A semi-extensive and semi-intensive pilot actions were developed in earth and pound system, the southern Atlantic area of Portugal and Spain. In Portugal, the experiment took place at IPMA's aquaculture research station at Olhão in Algarve, and in Spain at Estero Natural company facilities by CTAQUA at Porto Real in Cádiz, as Macarena said. The first image on the left is of IPMA facility. The area in blue is the reservoir pond, in green is the settling pond, and in red are the 6 ponds where the experiments took place. The arrows indicate the inflow and outflow water. The water came from Rio Formosa to reservoir pond, next for the experiment ponds, and later to settling pond, and come back to Rio Formosa. Each pond used for the experiment had a water volume of 750 cubic meters, each one, a surface area of 700 cubic meters, and a depth of 1.5 meters. The both images are, the two both images are from CTAQUA area experiment that was made in 2 ponds that the area is in yellow. These images show the integrated IMTA experiments. The 2 pictures above show the IPMA experiments. The left photo shows the fish and oyster pond. It's a water flow-through system with life support structures such as automatic feeders, aerator, and controlled water flow through pumps. The right photo shows the floating cages to uva cultivation in a different tank with the water inflow from fish and oyster pond. The second line of photos shows the CTAQUA experiments. The first photo is the fish culture. The second, the oyster culture within the fish pond. And the left one shows the macroalga floating cages in a different pond. The cultures was positioned in sequence, and the flowing water passed from fish and oyster pond to macroalgae culture. Differently from IPMA, CTAQUA uses the tidal for water flow, and there was no aeration. About the experimental conditions, at the IPMA station, 2 semi-intensive productions was implemented, aiming to compare the performance of 2 contrasting density levels, high and low. The experiment lasted 5.5 months, from April to September of 2018. The experiment used 5 species of different trophic levels, 3 fish, migri, white sea bream, and flat-headed mullet, oyster, and macroalgae. The design was 3 ponds for each system, low and high density, 2 ponds with fish and oyster, and a macroalgae pond in a semi-recirculation system, and controlled water renovation from reservoir ponds. The levels of dissolved oxygen, temperature, pH, turbidity, salinity, chlorophyll A, and nutrients were monitored. Oysters were exposed to air once a week, and oyster mortality was monitored monthly. Fish parasite was assessed every week. In September, the experiment was finished due to a strong amylodinium ocellatum outbreak, a parasite dinoflagellate. This infection led first to the increase of water renovation rates, and later to the use of copper sulfate to control the outbreak, with consequent impact on the phytoplankton concentration. These experimental conditions were organized in 2 initial densities of 1.5 kilograms per cubic meter on low density and 3 kilos on high density, with a provision of obtaining final fish density of 2.5 and 5 kilos per cubic meter, considering 1 cycle production initially planned for the experiment. This table shows the trophic levels of species and the initial biomasses per density system, high and low. The results As I said, the experiment lasted only for 5.5 months due to a strong amyloidosis outbreak. During high temperatures in summer, the parasite amyloidinium has good condition to proliferate. The infestation was probably due to a more susceptible health condition of fish raised at the density used by IPMA IMTA semi-intensive system. The production of the 3 fish species in kilograms was higher in high density system, while oyster and macroalgae, the higher production was on low density. The total animal production was higher on high density system, with gain biomass around 390 kilograms, means 30% higher than low density, approximately. The macroalgae biomass gain was higher on low density system. The mortality of migri and sea green was higher on high density system. Mullets had almost no mortality, and oysters present around 50% of mortality due to the reduction of microalgae concentration. The reduction of microalgae concentration was originated by the high water renovation to control the parasite infestation. This table shows water renovation and the feed conversion ratio, FCR. The high water renovation also led to the increment of feeding and therefore to the increment of CR in both densities. These were 4.4 and 3.2 in low and high densities. FCRs reaching 2.5 are the common values in semi-intensive pond aquaculture. The increment of feeding also led to increased aeration. The rise in water aeration and aeration increased energy consumption. To conclude, in this IMTA system, taking into account total production, high density system had higher final results. High trophic level species had higher production on high density system and lower trophic level species on low density. The densities applied on this IMTA system led to parasite outbreak. Parasite outbreak increased the water renovation and energy consumption and led to use of chemical treatments. High water renovation caused a reduction of microalgae concentration, oyster mortality, and increased feed rates and FCRs. So is that. And now I pass the word for Erik-Jan Malta that will speak about the experiment from CTAQUA. Thank you.
Okay, thank you very much, Gabriela, for presenting the Portuguese part of this pilot action. I will continue with the Spanish part of pilot action 3, focusing on the work carried out by CTAQUA. As said, I will present the Spanish part of the pilot that Macarena already presented. The company, Estero Natural, very important of these sort of evaporation ponds, that these are driven by a tidal movement. We had to do some slight modifications to the system to maintain a constant water flow, and also a constant minimum depth, which especially for the algae was very important. And it basically consisted of managing the sluices, so that now at high tide at spring tide, we take in a lot of water, which we store in the storage basins, the large reservoirs, the esteros. That guarantees a continuous flow through the compartments. So the experiment itself consisted of 2 compartments. One compartment we had fish, gilt-headed sea bream, Sparus aurata, and dorada in Spanish, together with oysters, Triosostrea or Macarena gigas. Fish are fed with a standard commercial feed. And then downstream, we have another pond with seaweeds. We're using 2 seaweed species, Ulva anoi and Yasilaya yacilis. So, and here you can see the initial densities, not too high. It's called improved extensive cultivation.
So 60 kilograms of fish, 15 of oysters to start with, 16 ulva and 4 gastralaria. Then we maintain more or less the algae biomass by harvesting them every 2 weeks. And we also adjust the oyster biomass by, well, we adapt every 6 to 8 weeks. Also not to get the density getting too high. Okay, some pictures. So you can see the oyster and fish compartment. As Macarena already commented, we adopted IPMA's technique of oyster cultivation, which is now become very popular also at this farm, of the the hanging bags. And you see also the anti-bird nettings for the fish parts. Then for the seaweeds, we tested 2 techniques. We started with long line cultivation, but as our ulva does not sporulate, we had to attach the algae ourselves, which is a bit of work. And later we found it easier to switch to these floating cages. In the end, we had 20 cages. They are 1 by 1 meter. And they float, they go up and down with the tidal movement. And we found this technique easier for seeding and harvesting. Some data on production. So we produced about 65 kilograms of fish, 363 of oysters, of which 94 kilograms was flesh, 23 kilograms of ulva, and 12 of gastralaria. So some notes and remarks with this production figures. Quite some fish escaped, especially with the highest spring tides. We had inundation of the ponds, and we saw fish escaping to other compartments as well. So this has reduced the final biomass produced inside our IMTA system. The oysters, as I said, the density was adjusted every 2 months, more or less, and the harvested oysters were seeded elsewhere in the farm. So they were not inside our IMTA system, but they were still used elsewhere. For the seaweed, the cages that we had suggested very high doubling times, especially in spring, in May and June. So about 1 week to 10 days for ulva and 40 to 20 days for gastralaria. So the production potential appeared to be very high. However, we suffered considerable losses, especially of recently seeded biomass. That was especially because we had some events where spring tides coincided with very heavy storms, summer storms, which are typical of this region, but not that early in the year. So we estimated we lost about 20 kilograms recently seeded biomass that did not grow out. So this suggests that production potential is much higher than what we actually got in harvest. So in this, yes, I will also now continue focusing a bit more on the trophic connection itself. These ponds are connected by water flow. So according to our IMTA definition, once you have the connection, it's an IMTA. But we of course wanted to really get more into the connection itself. So we took water samples. They have not all been processed as yet, but preliminary results and also the earlier work of IPMA in the publication of Emilia Cunha in aquaculture, they indicate the following general patterns. So an increase of nutrients and chlorophyll A in a fish tank, which is natural, of course, so by fish and oyster excretes, and also a decrease in turbidity, which is caused by the oyster filtration. Then in the seaweed tank, we generally find, especially if densities are high enough, a decrease in nutrient concentrations, suggesting the incorporation of nutrients by the seaweeds. So this was more or less as expected. We also wanted to look into some other markers. And there's two markers that you can use from the feed. That's the fatty acid profile of the feed and the stable nitrogen isotope marker, so the delta 15N ratio, which are both differing from natural food sources in the environment. So for the fatty acids, fish, of course, they eat the feed, and part of the fatty acid profile is maintained in the fish fillet itself, and also some of it goes to the fish excretes, which are then filtered by the oysters, and the oysters also filter directly fish feed rests. So you can expect the part of the fatty acid profile of the feed to be conserved in the fish and oyster compartments. Then for the stable nitrogen isotopes, this also through the feed goes into the fish and into the oysters, and the excretes of both of them will end up in the dissolved inorganic nitrogen in the water and in suspended solids. And dissolved inorganic nitrogen then goes to the seaweeds, who will incorporate it. So if the trophic connection exists, you should see part of this delta 15N signature back in all other compartments, in fish, in oysters, in dissolved nutrient suspended solids, and in seaweeds. Unfortunately, due to this, to the pandemic, all analytical labs have been closed down for a while. So we do not have the result yet. We only have some preliminary results from fatty acids, but they from IPMA, and they show that this trophic connection indeed exists. So you can find back part of the fatty acid profile of the feed. You can see it, of course, in the fish, but also in the oysters. So yes, it appears that connection exists, and we also hope to see it in the stable nitrogen isotopes. Okay, for some conclusions, so we can see these former salt evaporation ponds. They show a great potential for IMTA because of there are different compartments. They're relatively easy to manage. There's a good water flow. The water flow is assisted by the tide. It's tidally forced, so that there's no need for pumping, saving a lot of energy. At least for the oysters, we can see there's a very high production capacity. Seaweed systems definitely need to be improved. We are currently testing a different setup of these cages in a different project. We're also going to test these long line systems. Maybe we can trigger sporulation, or we can seed seaweeds in another way. And we see that the preliminary results of marker analysis and also of nutrient concentrations indicate a trophic connection between these compartments. So at the end, we are coming up with a kind of a standard model for this land-based semi-extensive aquaculture facility. So what we see, in order to successfully implement IMTA in this type of environment, it is very important to select species and systems that are adaptable to changes in water level, also to salinity and temperature dynamics that occur in these environments. Especially summers can be very hot, so evaporation will be quite high, and salinities will go up to 45 or sometimes even up to 50 PSU. So you need robust species able to withstand these conditions. The same goes for temperature, that also can increase to over 30 degrees. And at night, again, they will quite rapidly decrease. So you need species that are able to withstand these conditions. Also very important, these are extensive wetland areas, as Macarena already indicated, very important for migrating birds, for instance, and other animals and plants, and have a high diversity. So it's very important, and they're also connected, have an open connection to the sea. So it's very important to work with well, native species or species that are at least growing there for quite some time. So we have seen various fish species that we can work with these systems, and also we have seen oysters. There are other possibilities as well for other shellfish species, for instance, clams. For other seaweed species, there might be possibilities. And there are also experiments going on with new species for aquaculture, like the sea urchins and the sea cucumbers we have seen earlier. And you can also think of other species like crustaceans as shrimp that might offer possibilities to diversify more this system. So I would like to thank all personnel of IPMA and CTAQUA and all students that assisted in this pilot action. And with this, I've come to an end of my presentation.